Hello and welcome. Today I'd like to talk about experimental probability, and that's probability inferred from observed data. For our purposes, that's going to be relative frequency. So before we talk about relative frequency, let's just talk about frequency. What do I mean by frequency? So let's start with an example here. Say we're going to roll a standard six-sided die, and let's say we rolled it 600 times, and kept track of how many each side of the six-sided die showed up. So we could, just keep a running tally or a running list of the sides. Say we rolled a 1, and then we rolled a 3, and then a 4, and then a 1 again, and then a 2. I don't want to do this 600 times, right? I kind of just want to count how many times each number was rolled. So instead of that, let's just make a table. So we'll have our results here. 1, 2, 3, 4, 5, 6. And we'll count how many times each result happened in our 600 times. And we'll call the number of times each result is rolled the frequency. So let's say we rolled a result of 1 90 times, 2 112 times, 3 84 times, 4 92, 5 131, and 6 91. So you would think each of these results would, on average, probably occur about a sixth of the time. That is a statement of a fraction, 1 out of 6. And that's what we're going to do when we talk about the relative frequency. For each of these frequencies, we can calculate the relative frequency. I'll write it here. Relative frequency is just the frequency divided by the total. It's the frequency relative to the actual number of times we rolled this. So the relative frequency here would be 90 out of 600, which you could write it as a fraction, or we'll often see it as a percent as well. So either a fraction or a percent. Same thing with 112. We would get about 18.6 repeating percent. For the result of 3, we got 84 out of 100, right? 84 out of 600, and that's about 14%. 92 out of 600, that means we rolled a 4 around 15%, 15.3 repeating percent to be technical. 131 out of 600, that's 21.83 to 3 repeating percent. And finally, our result of 6 is 91, which is about 15% again, 15.16%. You could write these as fractions too, or as mixed numbers even. 18.6 repeating percent, that's 18 and 2/3%. The point is, these are relative frequencies relative to the total. And that way, if we say we did another experiment where we rolled a die, say 1,000 times, we could then find those relative frequencies and we could compare the two. We can compare the results from two different dice, say, to see if they produce similar results. Now that we have relative frequencies, we can express a probability, an experimental probability, that is telling us what fraction would we expect to get each of these results. So you can use this data here to predict what you might get in the future. And yes, there are statistical methods for this too to get better predictions. But for now, we're just going to use our experimental probability is going to be, it's just another way of saying relative frequency. So based on this data, and this is a key phrase, that means We're not looking for the theoretical probability of getting one of these results. We're going to just use the data that we've gathered from this experiment. Based on this data, what is the probability of rolling a 4? Okay, you might see shorthand probability of getting a 4. Just introducing it now so you see it. So that probability of getting a 4, that means based on this data, we just look at where 4 is. Looks like the data tells us we're looking to get a probability of 15.3 repeating percent. Depending on your rounding, it could be 15.3% or 15%. But yeah, probability of getting a 4 is about 15% or 15.3 repeating percent. 15 1/3% if you want to get technical here. That's the probability. Now, actually, we know that the theoretical probability, we'll talk about theoretical probability later, on average, like if we rolled this die, a fair die, 1,000,000 times, we should expect about 1/6 of those rolls should be a 4. Now, 1/6, by the way, is 0.16 repeating, or 16 2/3%. And so just from our experimentation here, our little experiment here, we get close to a similar percentages. Is that far enough away for us to say that this isn't fair? Well, maybe with probability getting a 5, that 21.83% seems pretty high, but we'd have to bring some other tools into this to determine if that's reasonable to still get that relative frequency from just sheer randomness. So that's one question. What other kinds of questions can we ask? Again, still based on this data, how many 4s can I expect to roll based on this data if I roll the die 5,000 times? Well, we can look at our relative frequency. These are fractions, right? 15.3% is a fraction. It's a fraction of a whole. It's a number out of 100, right? So you could take 15.3 repeating percent and multiply that by 5,000, since this is a fraction of a whole. Multiply this by our new whole, basically, and you'll get the part. And so you'll want to convert 15.3 repeating percent to an actual decimal before you do too much work with it. And so we would convert that to 0.153 repeating, or just use the original fraction, 92 over 600. Use that decimal and multiply that by 5,000. And we would get about, I'll use a little squiggle here on the equals just to say this is about 767 if we round it to the nearest whole. One more question, I'll put it here. Suppose I roll the die some number of times and get 724s. Based on this data, how many times did I roll the die? So now, in this case, we can see that 720 is the result we would have gotten if we would multiply our 15.3% repeating percent times our total, right? So here's a little idea here. If I got 720 by multiplying the total by 15.3 repeating percent, I guess we have to do what? To get this guy by itself? To undo that multiplication? Well, we would just divide. I'm going to divide both sides by 15.3% because I'm just teasing a little bit of algebra here. In this situation, those go away. 15.3 repeating divided by 15.3 repeating is going to be 1. So intuitively, it seems like, yeah, that part, the percent, or anytime you're taking a percent of a total, you'll get your part, right? So to undo that, taking a percent of something, we would divide instead. Divide our part by our percent, and that should get us our whole. That looks like we get 4,696 total rolls. Rounded to the nearest whole number because you can't have a fraction of a roll. Okay. Let's look at another application of this. So let's say we have a situation where we're trying to count the effectiveness of say a mammogram test, or really a test for any disease, but I'm going to use this example from the book. And say you have a bunch of people that have tested positive or negative for cancer, and we also have tracked whether they actually had cancer or not. After collecting these frequencies, we can make a table, kind of a two-dimensional frequency table. And our columns will be all the people that got either a positive mammogram or negative mammogram. And they either have, and we also have people either have cancer or do not have cancer. I'm just going to fill in some numbers here. So what this number here, 302 people had a positive mammogram and also turned out to have cancer. And here, 76 people had a negative mammogram and turned out to have cancer. Here, we'll see 6,130 had a positive mammogram and had no cancer. Meanwhile, we have 3,492 women that had a negative mammogram and had no cancer. So we could kind of get a feeling for what some of these mean and what it means for the test. You could say, well, okay, why all the positive mammograms and yet no cancer? Well, with these kinds of tests, you'd rather have a false positive and be wrong than miss a false negative. And these are what we would call false positives. These are what you would call false negatives. Better to err on the side of being positive than not. And if we had a lot of negatives, false negatives, that means a lot of people that actually had cancer would test negative, and that wouldn't be a very good test at all. But these are the numbers that we have, and we can add up these numbers along the rows and the columns. This row adds up to 378. This row adds up to 9,622. This column adds up to 6,432, and this column adds up to 3,568. So what these numbers, these totals of each row and column, they represent all the totals of that column, or all the total people in that row. And both of these should add up to the same amount. They add up to 10,000. Whichever direction we go, we better add up to the same number, 10,000. So now we can ask certain questions, a bunch of questions about this too. So for example, based on this data, we can ask simple questions like, what percent had positive mammograms? What percent had positive mammograms? That means percent of the total, of all 10,000 tests, right? So you put the total on the bottom, and up top you put the number that had positive results. And you can calculate that percentage. Should be about 64%, as you'd expect. 64.32%. So that's that. Now, if I wanted to then make a prediction based on this information, well, what's the probability that you'll get that a random person in the future, random woman in the future, will get a positive mammogram using this test? You can say, well, it's going to be the probability of that occurring is going to be about 64%. Now that includes those that actually had cancer and those that actually did not have cancer. So that tells you something about just how, the rate that you would get a positive mammogram with this test. So another question: what percent ultimately had a cancer diagnosis? Well, how many people had cancer in this? 378 out of a total of 10,000 again. And again, that's about equal to 3.8%. Now, where this table can be really useful now is to answer a question like this: what percent of women who had cancer tested positive? What percent of women who had cancer? Well, those that had cancer is this category here, this row here. Within that category, that row, how many of those tested positive? 302 out of a total of 378. And that's about 80%, I think. So, but what that tells us is that within this group, those that had cancer, the test caught it 80% of the time. Not to be confused with another question: what percent of those who tested positive had cancer? Now we're talking about this column. Of those who tested positive, that's this column, had cancer? Well, that's still the 302, but it's a different total, 6432. So that's going to be about 4.7%. So this first number, 80% here, kind of tells us how accurate is this, or one form of accuracy for this test. It catches 80% of those who are diagnosed with cancer. This bottom number tells you the probability that you have cancer if you tested positive. Because of this, you could say, well, just because you tested positive doesn't mean you necessarily have the disease. And that's because of all these false positives. So that's why you get multiple tests. You can describe any of these percents as probabilities given the right wordings. For example, this bottom percent is the probability that you have cancer given that you tested positive. That's what this vertical line means. We'll get into that at some later date down the road, or you might see it later in future classes. But this is just shorthand for probability that you have cancer given that you tested positive. And that's enough for now. See you next time.